You should be able to answer this question. We're going to give you a 2D grid of oranges. Each index of the array can have one of three states. If it's 0, the index is empty. If it's 1, the orange is fresh. And if it's 2, the orange is rotten. Each minute, a rotten orange infects its fresh adjacent neighbors. We want you to return how long it takes for every orange in the matrix to be rotten, or -1 if it's impossible. Okay, how's this? What if I just scan the array and check every orange at each minute? Every minute, I'd look at all the rotten ones and then just rot the fresh ones next to it. Then repeat the scan over again and over again until we reach a point where nothing changes from the last one. That might work, but what's the downside? We walk through the entire grid each minute. That's potentially rows times columns times minute time complexity, which is way too expensive. Is there a better mental model for this? I think we can actually solve this using a multi-source breadth-first search. Instead of rescanning everything every minute, we treat every rotten orange as the starting point in a queue. Then we have multiple BFS sources firing at once. Right, walk me through that. First, we scan the matrix and push every single rotten orange into a queue. We're gonna do that by just pushing a tuple of the coordinate, like row and then column. This is the index of a rotten orange that can spread the infection. Then we're gonna run breadth-first search level by level. We're gonna perform in-pop operations where in is the length of our queue at that minute. Then we're gonna look up, down, left, and right from that index. And if the orange is fresh, we're gonna add it to the end of our queue, changing the state from fresh to rotten as we visit them. After we reach the end of those first in iterations, we just increment our time variable by 1. It's been 1 minute. Why does this approach naturally track the time? For this, we're gonna explore out layer by layer from every single rotten orange in our matrix. This approach naturally tracks the movement of the infection outward in layers. That's why after each internal for loop, we increment the time variable. And what about the final check? Good catch. After BFS finishes, we need to scan the array one more time. If there are any fresh oranges left, that means they're unreachable. Therefore, we return -1. It's impossible. Otherwise, we return time -1. This is the total infection time. Great, what's the final time complexity? It's O of rows times columns. Every cell is touched at most 3 times. 1 in the initial scan, 2 in the breadth-first search, and 3 in the final check, which is linear. Perfect, you got the job. I'm making a video like this each and every day to help you improve your pattern recognition for software engineering interviews. If you found this video helpful, drop me a follow. I'll see you tomorrow.